Hello, my name's Clinton, and I'll be your guide through this final module of Day 5. We're going to talk about rational functions. Please don't forget to pause this presentation at any time if you need a bit more time to think about something. In the last two modules, we looked at polynomials. In particular, we saw how to perform long division of polynomials and how to factorize them and find their roots. Now we're going to talk about rational functions. A rational function is just a ratio of two polynomials. In particular, any polynomial p of x is a rational function because it's just p of x over 1. We're going to study the basics of functions of this form, together with their graphs. The domain of a rational function, that is, all of the x values that it makes sense to put into our function, is precisely the collection of all x values which do not give 0 when we evaluate q at them. Indeed, if we did find an x with q of x is 0, then we would be dividing by 0 when evaluating the rational function at x, and dividing by 0 is bad. Let's see some examples of what rational functions can look like. The function x squared over x squared minus 4 is a rational function. Both the top and the bottom of this fraction are polynomials. Its domain is all real numbers except 2 and minus 2, as these both make the bottom 0. This function, which you've seen before, is also a rational function. The top is the particularly simple polynomial the number 1, and the bottom is the particularly simple polynomial x. Its domain is all real numbers except 0. We're going to draw basic sketches of rational functions by thinking about the following information: the behavior of the function as x gets very large, either positive or negative, as well as the behavior of the function as x approaches points where the function is undefined, i.e., the roots of its denominator. These values can give what are called asymptotes of the rational function. The formal definition of an asymptote looks a bit scary, but it's not too bad. If a function f of x approaches some finite number L as x tends towards infinity or to negative infinity, the graph of y equals f of x has a horizontal asymptote. This picture gives a good idea of what's going on. As does this example. The line y equals 0 is a horizontal asymptote for the exponential function y equals e to the x, since as x tends to negative infinity, e to the x tends to 0. Of course, e to the x is neither a polynomial nor a rational function. On the other hand, if the function value itself approaches infinity or negative infinity as x approaches some finite number k, then the graph has a vertical asymptote, as this picture demonstrates. As an example, the line x equals 0 is a vertical asymptote for the function y equals ln x, because ln x approaches negative infinity as x tends towards 0. Rational functions may, but do not necessarily, have vertical asymptotes at the roots of their denominator. This is because if qx is 0, px on qx is px on 0, which may tend to infinity or negative infinity, as given in our definition of a vertical asymptote. If px and qx have common factors, these factors cancel out, so will not give rise to asymptotes. The function is still undefined at these points. Let's look at an example of curve sketching to see some of these ideas in action. Consider the graph of the function y equals x squared over x squared minus 4. Let's think about all of the information we know about this function. It's even. That is, f of minus x is equal to f of x for all x. This means its graph will be symmetric about the y-axis. The curve also passes through the origin, and it's undefined for x equals 2 and minus 2, because both of these values make the denominator 0. As x gets closer to 2 from above, y tends to positive infinity. Since then, x squared minus 4 will always be greater than 0, and the numerator is always positive, as it is a square, so the whole function will be positive. Also, as x gets closer to 2 from below, y tends to negative infinity, since then x squared minus 4 will always be less than 0. This means x equals 2 is a vertical asymptote of the graph. It's also easy to see that as x tends to minus 2 from below, y tends to infinity, and as x tends to minus 2 from above, y tends to minus infinity. Hence x equals minus 2 is also a vertical asymptote of the graph. We should also check what happens as we make x very large, positive or negative. We can divide all terms in the fraction by x squared, which shows that as x becomes large, positive or negative, the function tends to 1, which means the line y equals 1 is a horizontal asymptote of the graph. Let's have a look at what else we can discover about this graph using calculus. Differentiating x squared over x squared minus 4 using the quotient rule gives that the derivative is the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared, which simplifies down to minus 8x over x squared minus 4 all squared. You should check this. This is positive when x is negative, and negative when x is positive, since its sign is determined by the minus 8x factor, as the denominator is always positive. Except, of course, when x is 2 and x is minus 2, when the derivative is not defined. The derivative is only 0 when x is equal to 0, and we have already done a sign test above showing that this is a maximum turning point. Let's use all of the information we just found to sketch this graph. First, the vertical asymptote at x equals 2. Now, the other vertical asymptote at x equals minus 2. Now, the horizontal asymptote at y equals 1. We know that as x tends to 2 from above, y tends to infinity, and as x tends to infinity, y tends to 1, so we can fill in this part of the graph. We saw that the graph passed through the origin, and our differentiation showed us it had a maximum turning point there. Finally, we saw that as x tends to minus 2 from below, y tends to infinity, and as x tends to negative infinity, y tends to 1. So this is what our graph looks like. Here are some practice questions asking you to follow a similar procedure and sketch some rational functions. Remember to find out as much information as you can using all the different techniques we've studied. Press pause and then press play when you want to continue. Here are the answers.